Okay, hi. So we're going to we're going to start a new chapter today. The first section of width is on vectors in Rn. Now, this is something, again, that you're probably familiar with from Calc 3 if you've taken Calc 3. If not, it's not all that big a deal, but there's one big concept in here toward the end that is really important that you may or may not have seen. All right, so let's just start off. A vector in n-dimensional space, so in Rn, is an ordered n tuple of numbers, right? So we write that just like a point, right? So you notice here, you may be used to seeing brackets around that, or you might, instead of seeing a bold-faced letter here for the name of the vector, you might be used to seeing X with an arrow over it. That's what we'll do in the classroom because it's hard to write bold versus not bold and have you tell the difference. But you'll see those two interchangeably used. And X1 through Xn, all of those are just real numbers. All right, so if you collect them all together, we call that space Rn. All right, so you have this geometric way in R2 and R3 of visualizing a vector, right? You always think of it as a directed line segment starting at a tail and emanating to a point, right? So for instance, in R2, if you think of the vector, let's call this 3, 2, this is X, this is Y. Whoops, can't see it. Here you go. Here's 3 and here's 2. So the vector 3, 2, you can think of as a directed line segment that starts at the origin and whose head points towards that point 3, 2, right? So that's a way of thinking of a vector. And sometimes it's actually quite useful in R2 and R3 to draw them that way, right? And especially when you're dealing with forces and that sort of thing. All right. The X1, the X2, all of these guys are called the components of the vector. And sometimes what you'll see, especially in linear algebra, is that you'll see this vector written as a column vector, right? So depending on the situation, we might use a row with n columns or one column with n rows, right? These are meant to signify the same quantity, okay? This is called a row vector. This one here is a row vector for obvious reasons. It's written as a row. And this guy is called a column vector for the same reason. Okay, so two operations on vectors with which you're likely familiar are how you add them and how you scalar multiply them, right? So we know that the two vectors that you're considering have to have the same number of components from these definitions. I mean, because you can't even, if you have different number of components, you're not going to be able to form a vector by adding corresponding components, for instance, right? If one has fewer than the other, there's going to be a component that's not defined, right? So these are vectors in Rn. You cannot add or subtract or deal with vectors in any way unless they're in the same space. Okay, and we'll let C be a real number. Okay. So in terms of a picture, let's draw one over here. I'm just going to use R2 for an example. Right, so you always think of drawing the vectors so their tails from the origin, right? So I'm going to represent my vector, let's say U, as that guy, and I'm going to draw a vector V also from the origin. Different, it could be a scalar multiple, who knows, but just some other vector V. And what I want to recall is something called the parallelogram rule, if you will. It's a way of seeing what the sum and the difference vectors look like geometrically in R2, right? So a vector can be translated, right? So this picture, if it's at the origin, the head of the vector is the vector, right? So it is that point. But I could also translate it as long as I keep the so-called length and direction the same. I can translate that vector and mean the same thing. It still holds the same information. And same way here, I can translate U, right? So if I translate in that way, keeping the directions the same and the lengths the same, that forms a parallelogram, right? Opposite sides are parallel and they have the same length. And so notice that in here, I can form the two diagonals, namely from the tail out here. Okay, so I can form that guy. And I can also form this one. Okay, and notice I'm being deliberate with the arrowheads. If you reverse them, we'll see what that means geometrically. But for now, you can form those two. All right. What it turns out, in terms of adding vectors, you can think of it as a total resultant, right? So a total sort of compilation or result of adding components together. So in terms of adding u plus v, here you've gone this far for u, and you've gone this far for v, right? So in the x direction, that's u1 and v1. And so the x component of the sum ought to be u1 plus v1. And then same in the y, I've gone this far in terms of the v vector, and this far, in terms of the u vector. And so this whole thing here should be the y coordinate of the sum vector, right? So that geometrically, that would suggest that the red vector there should be geometrically u plus v. Okay. The other vector, we have to talk about scalar multiplication, right? So u plus v, we know that we add corresponding components together. That's the definition. And it's rooted in how you want to think of adding vectors in an application, right? So in terms of total distance traveled in the x and the y direction, think of it that way. Scalar multiplication, if I multiply a vector by a number, could be positive, could be negative, could be zero, right? You simply multiply each of the components by that number. All right. And we'll look at what multiplying by negative does in a minute. Here, if I were to reflect, so we know that, let's just take an example here. Let's just call u equal to 1, 0, very simple. And if I multiply that by a -1, I multiply each of the components by that, right? So u is this vector, negative u is that vector. Notice they have exactly the same length, right? They both go one unit in the x direction, nothing in the y, but they point in exactly the opposite direction, right? And so in essence, you can think of multiplying by a -1 as simply reflecting the vector through the tail, right? So if the tail's at the origin, you're reflecting it over through the origin. So over here, let's go back to our picture. I need another colored pen. This was our vector v. This is our vector u, right? So if I want to think of this vector, notice I went, if I were to, let me get this off my pen, or is it ready? Oh, never mind. If I were to add these two, so if I add this vector plus whatever this guy is, so I have v plus our question mark vector, that has to equal our vector u, right? So apparently that's just by our addition rule that we just said. If you connect the tail of the beginning to the head of where you ended, that's what we did here, right? We started here, we went there to there, we connected the tail from where we began to the head of the vector where we stopped, and that turned out to be the sum vector. Here, if I do the same thing, I start here, I went to v, and then here. So if I connect that tail to the head, I get the vector u. Therefore, if I just solve for my question mark, the question mark vector has to be the difference u minus v. It has no choice, right? So this vector here, just from our addition rule, has to be that. All right. Had I had it pointing in the opposite direction, that's where this comes into play. Oops. Right. So if I start here and go backwards, the same length occurs at just exactly the opposite direction. The other vector pointing that way would be v minus u. All right. And then if I start here and point that way, that would be v, or negative u plus v. All right. So just kind of some geometry there to kind of help visualize if you're a picture-oriented type person. Let's actually compute, just for so we know how to use the formulas. So u plus v, notice we have two vectors in R2, so we can add them. And we're going to add them component-wise. Even though we stated the definition as a row vector, remember we can go back and forth between row and column as long as all vectors are one type in a given computation, right? I can't add a row vector and a column vector together, right? They're different matrices. But I can add these guys by simply adding the components. All right, let's look at 2u. 2u means to multiply the components of u, each of them by 2. So I get 6, 2. Now, if you were to plot that, let's see, 1, 2, 3, here is 3, 1. 6, 2, 1, 2, 3, 4. We're out here. You'll notice that 6, 2, and 3, 1 lie on the same line. And this vector here has twice the length of the original vector u. You can check that out, right? And so what this tells you, a scalar multiple, if it's positive, you're going to get a scaling factor of that vector. So if it's larger than 1, the resulting vector will have a longer length than the original guy. Same direction. If it's between 0 and 1, it'll shrink it down. If it's negative, you do the same sort of thing, but then you flip it over the tail, right? So a negative 2u would go back this way, back this way 2 units. So it points exactly the opposite direction, but would have the same length as 2u. All right. And then u minus v, you can think that's not really a new operation, right? It's just u plus a negative v, right? So you can define subtraction as addition. And we know how both those are defined, right? U is 3, 1. Negative v, you multiply the components of v by negative 1. And so now if you add component-wise, you get 2, negative 1. Okay, and you have that picture that you can draw for those specific vectors. Okay. All right. Putting it together, now we have two vectors in R4. There is no picture, right? So there's no geometry to rely on here to motivate how you would add these. So we have to just use the definition that we've formulated. All right, so what we know is you have to first multiply, right? So I'm going to write these as column vectors. You don't have to if you don't want to, but I'm going to save room. And oops, and then I need to multiply v times 3. All right, so I'm just plugging in what u and v are here. And now I know that I can multiply each of those components by 7. And each of these guys by 3. Okay. And then now I add component-wise to get that vector out. All right. So what this is called is a linear combination of u and v. Right? We're going to define that momentarily in precise terms. But notice all we did was we took u and v, we multiplied each one by a scalar and added them up. That will produce a linear combination. Next, let's take a look. It's kind of a short section, but it has a very important definition, which is here. Right, so in general, we just mentioned what linear combination was for two vectors, but you can use the same definition for n or m vectors, doesn't matter. So if I give you m vectors and they're all in the same space, right? So these are in, let's say, Rn. And you have scalars, so just real numbers. If I multiply each of these vectors by a scalar and add them up, that produces a linear combination of those vectors. In particular, that's another vector, right? That vector is in Rn because of our addition and scalar multiplication were closed in the sense that if you added two vectors in Rn, or if you multiplied a vector in Rn by a scalar, the result was again in Rn, right? So I know that this is going to produce a vector in Rn. All right, so now you might have seen this in Calc 3 or in your physics classes or whatnot, but oftentimes what you think of, let's just think in R2. Let's take this vector u, which is, let's say 5, 2. Okay, sorry about that. So you have a vector in R2, 5, 2. And what you can do is you can break it down into its components, right? You have, if you think about it in terms of addition, I would take that vector and I would then add it to this vector to get there. Makes perfect sense. This vector here is 5, 0. You had to have gone 5 units in the x direction to get there. Right, so 5 times 1, 0. And then from there, you had to go 2 units in the vertical direction. Remember, though, I can translate these vectors, right? So this vector back here is 0, 2. Well, this vector is also the same thing, or I should say 2 times 0, 1. All right. They are the same vector, but when you add component-wise, you always take the vectors from the origin. So I would take this, I would translate it back to get this point. That point is 2 times 0, 1, because I didn't move in the x direction here. I just moved up 2 units. All right. And notice that if I add those two, 5 times 1, 0 plus 2 times 0, 1, that is my vector u. That means that u can be written as a linear combination of those two vectors. And in fact, that's true no matter what vector you give me in R2, right? No matter where you are, you could always go in the x direction, then in the y, up or down or left or right, and you'll always land there using these two vectors, right? So we'll use the term basis later on, but these two vectors here are enough. They're kind of a skeleton for R2 in the sense that everything else in R2 can be written in terms of scalar multiples or linear combinations of them. Okay, so let's actually look at this example. This is prototypical of what we do in linear algebra. So you have a vector in R3, and I want to write it as a linear combination of these three vectors, if it's even possible. All right, so what I want, or if it is a linear combination of those, can we find scalars? And I'm going to call the scalars this time x1, x2, and x3, because those are going to be the numbers we're trying to find, right? And so when we're trying to solve a system, the solution vector tends to be in terms of x1, x2, x3, or something like that. So instead of c1, c2, c3, which you can do, I'm just going to use x1, x2, and x3. So can we find scalars x1, x2, and x3 such that b, this vector b, is x1 times u1, right? So I multiply a scalar times the vector u1, multiply u2 by a scalar, and u3 by a scalar. If you can't find such scalars, then you can't write b as a linear combination of those vectors, plain and simple. But let's look at this in matrix form, right? So here, I'm going to put these as column vectors. Okay, so I have that is b. I have a scalar x1 times u1 is this vector, plus a scalar x2 times, u2 is this vector, and then plus a scalar x3 times this vector. All right. And so now if I simplify this, I'm going to write it as a system. Remember how to scalar multiply vectors by numbers. I multiply everybody in there by x1, everybody in there by x2, everyone by there in x3. I'll have 3 vectors in R3 that I can then add component-wise. And so let me just do that. Just reading straight across, I have x1 minus 2x2 plus 3x3. That'll be the first component of the sum vector on the right side. That has to be minus 2. 2 vectors are equal if and only if corresponding components are equal. Okay, so it has to be minus 2. Over here, I have negative x1 plus 3x2 plus x3, that's equal to 4. And then from the last one, I have 2x1 minus 3x2 plus 10x3, that's equal to minus 2. Okay? So that is the system. Let's actually write this in terms of an augmented matrix, right? Because we're going to have to find, we're trying to solve this system, and the solution would be these scalars that we're trying to find. So in terms of an augmented matrix, and I could have gone here directly, but I wanted to show the system. We're just going to peel off the coefficients like we normally do. Okay. So there's our augmented matrix. And what I want to do now is put this into echelon form so that I can solve the system. Let me get another piece of paper out. Aha. All right, so let me just copy this down just so you can see. Oops. Sorry about that. Again, maybe by the end I'll have this get used to this. 1 minus 2, 3, minus 1, 3, 1, 2 minus 3, 10, and minus 2, 4, minus 2. Let me enlarge that so you can see. Okay, so I want to solve this. So what I want to put this in echelon form. So I'm going to keep this 1 here. That's good. But I want to kill off the -1 and the 2. So what I'll do is I'll simply add row 1 and row 2 and replace row 2 by that. And then I'll also multiply row 1 by -2, add it to row 3, and replace row 3 by that. All right, so if I do that, let's actually go through. I'll leave the first row intact. The second row, if I multiply everything here by -2 and then add to that second row, what I will get, and you can check me on this, is 0, 1, 4, 2. And then same thing here, multiply everybody in here by -2, add that to the third row to get 0, 1, 4, and 2. I think I might have misspoke here. Here you're just adding these rows, pardon me. So adding those, not multiplying it by 2 for this guy. I think I misspoke there. So if you just add those, you get this row. If you multiply this guy by -2, you get that guy. Okay. But now look what happened. We have the first row's fine, second row's fine, but this is exactly the same as that second row. And so what I'm going to do, anytime that happens, you're going to get a 0 row. So I'm going to simply subtract R3 minus R2 and put that into R3, right? Because I want all 0 rows to be at the bottom. And so the matrix that gives us is 1, -2, 3, -2, 0, 1, 4, 2, and then a row of zeros. All right, but that is in echelon form. That's all we need. We didn't say we had to go to reduced row echelon form. That would require, remember, that guy being 0, right? Because the pivots are 1 and 1. All right, so let me actually identify those. The pivots are here. That means that guy has to be free. And that's the only free variable, because the minute it's free, I can solve that guy, and then I can put both those up here to solve for the first one. So there's only one free variable. We'll call x3 equal to, well, I'm going to use s1 just because I want you to get in the habit of using subscripts. And then from this equation here, I know that x2 minus 4x3 is 2. And so let's plug in s1 for x3. And then solve for x2. So x2 is 4s1 plus 2. All right. Oh, that should be a plus. Sorry, that should be a positive. Positive, negative. Sorry about that. Okay, and then if I plug both these guys in here, I get x1 minus 2 times minus 4s1 plus 2 plus 3 times s1, that's equals minus 2. Let's simplify. Multiply both of those by -1. So I have x1 plus 8s1 minus 4 plus 3s1 is minus 2. Combine these guys. I have x1 plus 11s1 minus 4 is minus 2, and then just take these guys to the right. So x1 equals negative 11s1 plus 4 minus 2 is plus 2. All right. And so we have infinitely many combinations of these scalars, right? Those for S1 in R, right? So X1 is this guy, X2 is this one, and X3 is S1. S1 could be any real number you want. And so remember, our only goal was to rewrite B. So our vector B, go back here. Our goal was to write B as a linear combination of these guys. So let's just choose a particular S1. Why not just choose S1 to be 1? Let's fold this. Right, so if I chose X1 to be 1, then we have X1 is 2 minus 11, which is negative 9. X2 is 2 minus 4, which is minus 2. And X3 is 1. And so our vector B can be written as a linear combination of those three vectors. One possibility is this. Negative 9 times U1 minus 2 times U2, and then plus U3. Okay, so the answer is yes. So what we're going to do in the next section is kind of an expansion, kind of interesting, expansion. Oh, I thought I had a pun, because we're going to talk about expansion. But anyway, bad pun. But anyway, we're going to look and see if every vector in a space can be written as a linear combination of a set of vectors, right? If it can, we'll say those vectors span the space, so to speak. So it's going to be the same question, but now kind of a step up in terms of what we're going to exactly ask. All right. But in the meantime, give the homework in section 2.1 a go, and let me know if you have any questions. All right, bye.